Okay, our next speaker is Karsten Heeger, long-term collaborator of Stuart's, going to talk about precision studies at the Neutrino frontier.
Okay, well, thank you, John. Well, first, let me thank the organizers for the invitation to speak at this very special session. And my talk will be on measurements that Stuart has done. Jerry talked about the issues that Stuart clarified. And what I'd like to do in my talk is talk about the measurements he has done in neutrino physics and some directions he has set for us for the future. Before I start, let me say that I first encountered Stuart when I was a graduate student in Seattle. And I then moved on to become a postdoc at Berkeley in his group, and I then had the privilege to work with him for about 10 years since then. And it's probably fair to say that one cannot underestimate the impact and influence Stuart had on young people. And I know there are several of us here in the audience who have worked with Stuart during this neutrino time. Neutrino physics has come a long way since the early days. When I entered neutrino physics, we were faced with problems. The solar neutrino problem, the atmospheric neutrino anomaly. And these anomalies persisted for a while, several decades in fact. A number of experiments were done to do oscillation searches, and they produced a great variety of results and constraints that essentially created a very confusing situation in the 90s and up into 2000. And then following 2000 and the measurements that were done by Snow, KamLAND, and other experiments, we entered the era of precision neutrino physics. And it was during this time that there were several milestones along the way that Stuart set and where he had great influence. In the early days, when I was working on the solar neutrino problem, I learned about Stuart from his measurements of the boronate neutrino spectrum and the prediction of the solar neutrino flux. And following that, the KamLAND experiment got started that made the first terrestrial measurement of neutrino oscillations that were observed with solar neutrinos. It was about 2004 that a very influential study was led by Stuart, so-called neutrino matrix, that set the directions and the priorities for the field for the coming years. And two of the priorities that came out of it in the non-accelerator neutrino side were continued studies with reactor neutrinos, measurement of theta 1,3, and also the search for neutrinoless double beta decay. And two experiments that Stuart and his group were involved in were CORE and KamLAND then. Solar neutrinos were the early days of neutrino physics. The idea was to use neutrinos to actually look inside the sun and verify that light element fusion reactions are taking place. This fusion process had been proposed by Bethe in 1938, and then Pontecorvo and Alvarez had suggested that one can detect these neutrinos through the reaction on chlorine. And of course, as we all know, Ray Davis set out to build the first detector, and John Bacall started the solar model calculations. Now, in our understanding of the light element fusion reactions inside the sun, there are several processes that produce electron neutrinos. So the sun is a pure electron neutrino source. And these are the neutrinos that we can detect in the subsequent solar neutrino experiments. Now, a number of experiments studied the neutrinos from the boronate decay, and so understanding the energy spectrum of neutrinos coming out of this decay was important for the subsequent work in solar neutrino physics. Now, the solar neutrino deficit was first established by Ray Davis with the chlorine experiment at the Homestake mine. He set out to measure electron neutrinos from the sun, and he found a deficit over the more than 20 years of running of the experiment in the Homestake mine. The fact that there were too few electron neutrinos observed from the sun was not only limited to one experiment. A number of experiments were done with different targets, gallium, water targets, and eventually heavy water. And they all established that there seemed to be a discrepancy between the predictions from John Bacall and others and the actual measurements. Now, the experiments that were done were sensitive to different parts of the neutrino spectrum from the sun. And experiments like water-based super K and SNO, they measured the boronate neutrino spectrum. This was the prominent neutrino source that they were sensitive to. And so understanding this was an important issue. Now, in trying to predict the neutrino spectrum from boronate, you are faced with the situation that you have a very broad ground state that's unstable and decay into two alphas. And over many years, Stuart and collaborators worked on understanding this and coming up with essentially the reference measurement. And what I'm showing here is what nowadays is still considered by many the reference measurement. It's a measurement that Stuart and collaborators, including our chairman, made. It involved essentially the implantation in a silicon detector, and then you would measure the energy deposits from the alphas, and you also have a scintillator to detect the positrons coming out. So they made the measurement of the alpha spectrum, and from that they could actually deduce the boronate neutrino spectrum. This was not an easy measurement, and in fact it was an activity that spent a couple of decades. This is a paper from 87 where Napolitano and Freedman looked at this, and until late last year this issue was not settled. Stuart was involved in understanding, commenting, and discussing critically the measurements that determined the boronate neutrino spectrum. Now, the solar neutrino problem was eventually resolved by the SNO experiment that was independent of that prediction. It made not only a measurement of the electron neutrinos coming from the sun, but from the total neutrino flux by having sensitivity to the neutral current interaction. And this was first resolved in 2002 when SNO demonstrated that in the neutral current channel, the agreement with the solar model predictions is very good, but in the charge current and elastic scattering channel, you see the deficit, which was the indication of neutrino flavor change. And of course, all of you have seen the iconic plot that shows the three measurements from SNO, and that also show the agreement with the predicted boronate neutrino flux. Now, putting this into context, this is essentially the SNO charge current spectrum that was measured, and this is the boronate neutrino elastic scattering spectrum with and without oscillations. And the issue of what spectrum to use was revisited a couple of times throughout the years, and the last recommendation came in 2009 as part of a workshop, and that pointed to the reference measurement that I referenced earlier by Winter et al. In 2006. Stuart then went on to measure neutrino oscillations with reactor neutrinos, and in particular he led he was the co-leader of the US involvement in the KamLAND experiment. KamLAND was an experiment being built in the Kamioka mine, and it was designed to measure the integrated flux of antineutrinos from nuclear reactors all over Japan. And of course, this was possible while they were still running reactors. Now, when KamLAND was started, one should say, it was not clear what the oscillation parameters were that they were looking for. And so this was a little bit, of a gamble. So KamLAND was built to measure the flux of all 55 reactors at a weighted distance of about 180 kilometers. And the experiment is that if you know the thermal power output of the reactors, and by knowing the isotopic field composition, you can predict how many electron antineutrinos you expect, and you try to count those with a detector far away. The KamLAND experiment was situated in the Kamioka mine. It's a 1 kiloton liquid scintillator detector, and it's built in a big cavity. And the neutrino interaction or the inverse beta reaction of the antineutrinos is detected with the PMTs inside that detector. Now, I should point out, as I just remarked, that before the measurements of SNO and KamLAND came along, solar neutrino experiments had allowed different solutions. And in this plot that I introduced earlier, which is essentially a plot that shows the parameter space of the mass splitting versus the mixing angle, two of the oscillation parameters that describe neutrino oscillations, several regions had been identified as allowed: large mixing angle, small mixing angle, and so on. And it was not clear at the time which one would be the right oscillation region. Things became clearer when the SNO experiment made the measurement of neutrino flavor change from the sun, and then KamLAND could confirm this with terrestrial measurement of the oscillations. And the KamLAND experiment was quite clear about this. This shows one of the first results from KamLAND identifying the large mixing angle as the region of the preferred oscillation parameter space. And in the end, everything else was excluded. But this was a situation where at the time KamLAND was started, it was not clear what it would measure and if it was actually sensitive to the right parameter region. Some of the KamLAND highlights throughout the years: in 2003, made the first measurement of the disappearance of electron antineutrinos from reactors. This plot shows you here the measured flux as a function of distance. All previous experiments had not seen any deviation from the expectation. The dashed line shows you the prediction from the solar neutrino experiments. And this is what KamLAND measured. It was the first terrestrial observation that electron antineutrinos disappear. With increased statistics and more data taking, KamLAND then established that indeed oscillations are taking place. It observed not only a deficit of neutrinos, but a characteristic spectral distortion, which comes from the baseline and energy dependence of the oscillation. And if you put this together, it was the KamLAND experiment that demonstrated, for the first time, that in this parameter L over E, you have oscillations taking place. What KamLAND did was not just a demonstration of oscillations, but it was a measurement of a fundamental parameter that describes neutrinos. And what it did was a measurement of the mass splitting between two of the underlying neutrino mass eigenstates. In this picture, we show the arrangement of mass eigenstates of neutrinos. After the discovery of oscillations, the mass eigenstates are the fundamental quantity, and they are separated by some mass splittings. And by being sensitive to the spectral distortions, KamLAND made the best measurement of the so-called solar mass splitting of better than 3%. And that was, at the time, very complementary to what the SNO experiment measured in terms of mixing angles. KamLAND, of course, did more than just reactor neutrinos, and I won't go into all of the details here, but let me also say that having a very sensitive detector for antineutrinos, you can also look for neutrinos from nuclear decays, radioactivity inside the Earth. And it was in 2005 that the first observation or investigation of geoneutrinos was reported by KamLAND. And basically what you're looking for are neutrinos that are lower in energy, essentially around 2 MeV, and so they're at the end of the reactor spectrum. And so if you look at this in real data, you see a slide axis here. And this was the first observation of geoneutrinos with KamLAND. Now, I should say a few words about our work at Berkeley. And one of the projects that I worked on with Stuart as a postdoc there was building a calibration system. And several of the people from the audience here were involved in this. And this was a project where I first realized how much Stuart likes hardware work. He was very much hands-on involved in designing the system, trying to make it work. The challenge here was we have a 1 kiloton liquid scintillator detector, 13 meters in diameter with a balloon inside, and we wanted to essentially put calibration sources inside this detector. So this was a project that involved many of us at Berkeley. And I refrained from showing the early pictures of the device that we built when it was actually tested off the roof of the ADH and cyclotron. In the end, we moved it inside a high bay area and did some more professional testing. But the system was built and it was installed in KamLAND, and in the end, it helped us achieve the precision that KamLAND reported in its final papers. Now, Stuart was obviously involved through many phases of KamLAND. He was involved in the construction. He organized the US contribution to KamLAND. And these are just a few pictures of his work on site. And besides all the hard work, we also had occasionally the pleasure of doing collaboration meetings in Hawaii. And this was actually an excursion on one of the volcanoes. So I think the young people also enjoyed that. The impact of KamLAND was summarized in the National Academy's report, the decadal survey that Stuart led in 2010 to 2012. And it was after the observation of flavor change by snow, the terrestrial confirmation that the solar neutrino problem is solved. And this direct observation came from KamLAND. And that was clearly a reason to celebrate. Now, Stuart was also very influential in setting directions for the future. I mentioned that in 2004, he organized and led a multi-divisional study on the future of neutrino physics. And this is the cover of that study. It was called the Neutrino Matrix, and it really captured the growing interest in the community and the excitement that had come out of the recent developments in neutrino physics. And two of the directions that came out of the study were, one, understanding all the mixing angles, and in particular measuring the so-called last mixing angle, theta 1,3, and searching for neutrinos double beta decay, which would establish that Majorana masses are involved in neutrinos. Now, we have accomplished this first goal, and I'll say a few words about that, but we are still trying and working hard towards achieving this second goal that was set in this study. Now, what KamLAND had done was to measure the flux of neutrinos from reactors at a distance of about 180 kilometers. And over this distance, some of the electron antineutrinos had changed into other flavors, and so a deficit was measured at the KamLAND detector. And this is essentially what KamLAND reported here. It was the dominant oscillation. Now, we know that there are three neutrinos, three mass eigenstates, and accelerator experiments had also established the mass splittings. And so we knew that there had to be a second oscillation that corresponded to a different length scale. And this length scale we knew had to be about 1 to 2 kilometers. And so an effort started in 2003 to look into how reactor neutrinos could be used to detect this oscillation. And one of the insights that came out of the experiments, including KamLAND, was that doing an experiment with one detector is hard, and what you really would like to do is to get away from absolute efficiencies and absolute normalizations and do a relative measurement between two detectors, one that's near a reactor to normalize the flux and one that's further away. Now, when this was first proposed and people started talking about this, I remember Stuart telling me, and I'm paraphrasing here, you really don't want to make a 1% measurement by taking a difference between two large numbers. So he was very skeptical that this was a good way to actually do an experiment. Nevertheless, he himself got involved, and there was a study in the US of several groups trying to identify opportunities for a reactor experiment to measure this mixing angle theta 1,3. And out of Berkeley, we had an initiative to try and see if we could actually do a measurement close by. This is the Diablo Canyon nuclear power plant just south of San Francisco. And the idea here was to build a tunnel into the mountains and with two experimental halls to be able to measure over a distance of 1 to 2 kilometers this oscillation. And a number of studies were done. We held workshops, and during that time we also had the chance to explore California a little bit, hiked around in the mountains, sampled the local wine here. And in the end, however, this turned out not to be a feasible site, and other alternatives, including the Daya Bay site in China, were identified. Now, the experiment in the end went forward, and you're probably aware of the results. And with the Daya Bay experiment, this oscillation was measured and detected. The theta 1,3 mixing angle was determined quite precisely, and this is now the observation of electron antineutrino disappearance. Now, even though Stuart did not participate in the final experiment in China, I should say that certainly in organizing and focusing the US effort and the discussion in the US, he was very influential in the first years of this effort. Now, with this measurement, it was possible to complete the 3 neutrino picture. While the solar and reactor experiments had initially identified one region, and the atmospheric and accelerator beam experiments had identified another region of parameter space as the preferred regions for oscillations, with the measurement of theta 1,3, we now have the full picture of 3 neutrino oscillations, and we know what the component of the electron flavor to the 3rd neutrino mass eigenstate is. And so with this, we have essentially continued the history of reactor neutrinos in the US that started with Reines and Cowan, and then we had KamLAND in 2003 with the first observation of reactor neutrino disappearance, and then the theta 1,3 experiments. Now, let me say a couple of words about the second goal that Stuart had identified in the neutrino mixing matrix. This was neutrinoless double beta decay, a process that has been observed with 2 neutrino emission, but not in the 0 neutrino mode. The observation of 0 neutrino double beta decay would imply that lepton number is not conserved and that neutrinos have a Majorana nature. And Stuart's group was involved in 2 projects that are pursuing this goal. One of them is an upgrade of the KamLAND experiment, where xenon was loaded inside a mini balloon in the detector, and the KamLAND Zen experiment just reported last year first results both for the half-life of the 2 neutrino case as well as limits for the 0 neutrino case. Stuart was also one of the founding people of the US collaboration for Core, and he helped organize that effort. Core is a double beta decay experiment based on a bolometric principle, where we use tellurium oxide crystals cooled down to 10 milliK, and we are looking for the temperature rise from the nuclear decay to identify events that might be neutrinoless double beta decay. This experiment is currently under construction in Italy at the Gran Sasso lab. It will include 1,000 detectors, a ton of material, and 200 kilograms of tellurium-130 cooled down in a dilution refrigerator to about 10 millikelvin. And during the planning and construction of Core, one of the critical contributions was planning a stepwise approach. And Stuart pushed very hard that we should not just go from Neutrino to Core. We should have intermediate steps to verify that we understand what we are doing and to also have data to analyze, especially for the young people along the way. And Core 0 is now running. It's a single tower. And we are on our way to build the full Core experiment, which is likely to start taking data in 2014. So let me come to the end. Over the last decade that I've had the chance to work with Stuart, I've seen him make contributions in critical areas of neutrino physics. KamLAND was a major success under his US leadership. And he left us with the goal to fulfill the next step in the neutrino discoveries, the search for neutrinos double beta decay. And with the experiments that are now underway, with his initial leadership, well, hopefully in the next decade we'll see if neutrinos are Majorana particles. Thank you. That is a long and complicated story. But let me say that one of the reasons was that talking about neutrinos in the public was difficult, telling people that something comes out of a nuclear reactor, when for decades everyone said that nothing comes out of a nuclear reactor. Yeah, thank you for the comment, Hamish. Yeah, I tried to make clear with my choice of words, co-leader, that there were obviously others involved, and this talk was supposed to focus on Stuart's contribution. Well, there were a couple of things. I think clearly double beta decay he considered as a very important field. And this also shows in the fact that in the end he was involved in 2 experiments to do this. He did feel that issues like this reactor normally had to be cleaned up and clarified. So maybe this would be something that would go into Jerry's scope of talk. So I think he looked at where the inconsistencies were, and one of the things that, I mean, as a young person entering his group and seeing how he worked, I was continuously amazed how much attention he paid to all of the details, and whether it was the physics that he always got right or the hardware. And so the most important thing was to get it right.